But altogether, over the past 5 years since TESS was selected by NASA for flight, there's been over 1 million person-hours of effort that's gone into producing this marvelous machine, and what we're going to be sharing the results from today, and I think you'll have the same level of excitement that we have from what actually has come about. Before I tell you about the current status of TESS, I'd like to share something with you, if I can make this work. Here we go. If you were to imagine that you could find a new Earth-sized planet every month, one of the things that you might find is that 3/4 of the host stars for such planets would be M dwarfs. These are stars that perhaps are half the temperature of the sun, and they're very common. There's 3/4 of the stars in the solar neighborhood that are of this type. You might imagine that you'd also find planets orbiting binary stars. About half of the stars that we know of in the solar neighborhood are of this type. And furthermore, you'd also find that there would be a large number of planets that are somewhat larger than the Earth, these so-called super-Earths that we've been learning about over the past 10 years, at least in a beginning way. Because of the fact that it's going to be possible to make these observations and to share this information with the community as a whole, we've come to speak of TESS as being the People's Telescope. And it's the People's Telescope in two ways, one of which is obvious and one of which is a little bit more subtle. It's obvious that the taxpayers of this country have paid for this effort, and therefore they should have a lot of the information shared with them as soon as we know about it. But it's also critically important to astronomers because for all of the work that's coming up, especially for the Webb telescope, we need to know the properties of the planets that are in the solar neighborhood, because they're going to be the very best targets for Webb and also the missions that are yet to come. So in terms of TESS's role in NASA's master plan, this shows the location of TESS, which was launched in April, between Kepler and Webb. And it actually builds on the work that was done by Kepler, but more than that, it actually prepares the way for Webb when Webb launches in 2021. The very best targets that Webb will be able to spend time studying in detail spectroscopically are going to, of necessity, be the bright targets that TESS will actually find, and that means that they're likely to be in the solar neighborhood. This is what TESS actually looks like. This is the way the instrument and the spacecraft looked when it was being integrated and tested at Northrop Grumman Innovation Systems in Virginia just a little over a year ago. And what you can see in that conical structure in the middle are the 4 cameras that are key to the science that TESS will actually do, and you can also see the solar panels and then the dish in the center, which is used to bring back the TESS data over the Deep Space Network that JPL operates. One of the key things with TESS is that it's small. It's only about as tall as I am. It weighs about 300 kilograms. And it's very simple. There's only one deployable, namely the solar panel. So it should, and in fact it did operate very successfully because of the fact that we did not have a lot of complications to deal with. The difference between Kepler and TESS is shown in this graphic. Kepler actually looks out in a cone into the sky that covers only about 1/4% of the solid angle around the Earth. TESS actually looks more or less at 4 pi, and in so doing, it's much more able to pick up objects that are associated with bright stars, because when one goes out on a starlit night, the brightest stars are not necessarily concentrated in one particular part of the sky. And if you want to actually try to make this statement a little bit more quantitative, this is a graph that shows what was known both pre-tests, primarily from Kepler with the blue dots that are shown, and the circles that are part of this graph are proportional to the depth of the transit that one actually can see. And the distance is shown in the x-axis, and the planet radius is shown in the y-axis in this particular plot. So the large accumulation of blue circles at the right side are generally associated with objects that are quite faint and therefore hard to follow up. The objects that TESS will actually find are primarily as shown in the orange circles, and those are the ones that are going to be within a couple hundred or 400 light years, as indicated in this plot, of Earth. And those are the ones that are really going to be interesting not only for Webb, but for large ground-based telescopes that are being constructed now, the TMT, the ELT, and the GMT, that we're all going to hear a lot about in the months and years to come. So the thing I'd like to show next, and it'll help in understanding some of the results that we're going to be sharing with you today, is the way that TESS actually does its sky survey. So TESS is actually, once it's launched and in orbit, the cameras actually have splayed fields of view that extend from near the ecliptic to approximately the ecliptic pole. And the overall fields of view of the cameras are quite large. The combination of the four covers about 2,300 square degrees, so it's about 5.5% of the sky. And then the satellite actually steps around in 13 sectors in the southern hemisphere for the very first part of the mission, and then it shifts and moves to the northern hemisphere. So what we're talking to you today about are primarily just observations that were made in the first few sectors of the southern hemisphere exposure, and that's what's shown in this plot. The sectors in this display, which is in ecliptic coordinates, actually shows where we started on July 25th with sector 1, 2, and 3, and 4. And each of those sectors is about a month in duration. And so all the results today are just from those first few bits of data that we got from TESS. So it represents about 1/12 of the number of what we will ultimately end up with. Okay, so the other thing is, we've talked a lot about TESS as an exoplanet hunter, and it certainly is that. But in addition, TESS is very effective at finding many other types of objects. This slide actually shows the solar system objects that TESS can find. We've already seen more than 500 asteroids, for example, that have just been found as targets of opportunity without any great planning going into it. In terms of variable stars, we expect to find millions of these in 2 years. At TESS's sensitivity, which goes well below a millimagnitude, at a tenth of a millimagnitude, almost all stars that we're observing show some type of variability. So in this plot, what you can see is that if there's a check mark, we've already seen examples of this, but if the fact that some of these objects, some of these designations do not have check marks yet means the data has just not been looked through to find this particular object. And in particular, if you then look at the possible things that we expect to see for explosive and energetic extragalactic sources, we expect there are going to be thousands of such objects, and they fit categories from supernova all the way down to kilonova that one can expect to see that will be associated with gravitational wave events. Looking even further forward over the next few years, because of the orbit that TESS is in, it's in a lunar resonant orbit, and the orbit itself was designed to be extremely stable on timescales of decades to perhaps even centuries. So the orbital lifetime is not a challenge for TESS. So we've actually thought a little bit about what we would be able to do if the satellite continues to be operated as it is now over the coming decades. So the top bar in this chart shows where we are in the green section where TESS is in its primary mission, operating for 2 years. Right now we're formulating a plan for an extended mission for TESS that would take us out to 2022, late 2022. And at the same time, as you could see, going further down through that list, Cheops, which is a Swiss mission, Swiss ESA mission, will be launching later this year. JWST will be launching as indicated. LIGO is being upgraded, so the chances are going to be improved, that we'll be able to find correlations with kilonova that are identified through their efforts. LSST is coming online. LSST will have a sensitivity that is very great for objects that are fainter than 18th magnitude. TESS goes down to a little fainter than 19th magnitude, so the two missions are incredibly complementary in terms of the way that they're set up. Also, looking at the bar for the next generation large telescopes, they're all going to be coming in the same period of time that TESS will be able to help provide suitable targets for. And then finally, there's the European Plato mission that will be coming on in the latter part of this decade, and there'll be additional information, especially on astroseismology, that mission will actually be able to convey. So I'd like to just provide with a couple of takeaways. This lunar resonant orbit has been an incredible boon to the mission. It means that the operation can certainly extend out for the next 10 or 20 years, perhaps even longer, based on experiences that we've had with other types of satellites that are in these far Earth orbits that are not subject to some of the problems that come up in low Earth orbit. The spacecraft stability is really exquisite. We're actually getting precision in pointing, stability in pointing that's at the 10 to 20 milliarc second level. These numbers are a tiny fraction of a single pixel. The cameras are exquisitely focused, and they've stayed so for the entirety of the mission as it's been operated. The survey by sector is going really well, and as you'll learn from the results that Chelsea and Michael are going to be sharing with you in a few minutes. We're now we've just completed Sector 6 last week. So that means we're a quarter of the way through the entire survey, and the images have been delivered to MAST as well as supporting data products, and there's going to be a lot more information that will come from the community. And already in this meeting alone, there's been reports of something like in excess of 20 papers that are either already prepared or ready for publication. So TESS is really going to be an important part of our astronomical efforts, hopefully for the next decade and more to come. And the best is yet to come, so the torrent of data is really starting to flow already. Thank you. So the next person who will be speaking is Chelsea Wang, and Chelsea is working at MIT on the pipeline that was developed for quickly identifying objects that we have been able to find in the test data. There's another pipeline that's operating at NASA Ames called the Spark pipeline, and the complementarity of these two efforts has been quite extraordinary.
Hello everyone, I'm Chelsea Huang from MIT, and I'm really excited to be here today to tell you all about the first discoveries of planets from the TESS mission. From the first 3 months of data, the TESS mission has announced more than 300 planetary candidates, and more than 8 new planets have been confirmed or validated through archive posts or journal articles. Today, I will mostly focus on 3 of these planets with radius smaller than our own Neptune. And they all happen to be around stars that's about within 100 light years around our solar system. You all remember this beautiful first science image from TESS. That's the southern sky in the eyes of TESS. You see the beautiful Magellan clouds. And now you have the 3 planets whole star also noted down on this image. I'll first just briefly remind you about the Pymensis C and LHS3844b, which are the 2 planets we announced a few months ago. And then I will tell you about the new discovery system, which was on archive of just a few days ago. Pymensis C is the first transiting planet that TESS discovered and confirmed in its mission. It's around a really bright star. The star is actually visible to the naked eye if you go to a dark place in the southern hemisphere. The planet itself is about twice the size of Earth, and using archival data from the HARPS mission, we're able to determine the mass of the planet to be about 5 times the mass of Earth. It is actually only the second transiting planet discovered around a sun-like star within 100 light years of our solar system. We also know that in the same system, there's also a super Jupiter that is orbiting the star every 6 years on an elliptic orbit, and that has interesting implications on the formation paths of the system. The second planet, LHS3844b, is only 30% larger than our own Earth. But it's quite different from our own Earth. It's around a red dwarf that's only 15% the size of Earth. And it's also belonged to this really rare population of planetary system called the ultra-short period planet. 1 year on planet LHS3844b is about 11 hours Earth time. The surface temperature of this planet is quite high. We think the day-side temperature is hotter than 1,000 Fahrenheit, and it's likely a lava world. The lead author of this planet is actually sitting down among the audience, Roland. You should say hi to everyone. And now we come to the newest discovery that we're going to tell you about today. It is a sub-Neptune. We're just going to the star now. This is HD 21749b. It has an orbit period of 36 days. And it was newly discovered by Dan, who is sitting behind there. And this is actually the longest period planet that TESS just discovered. It is also the longest period transiting planet around stars that within 100 light years of our solar system. With great effort from the PFS team, their representative also sitting in the audience, and archival data from the HARPS team, were able to measure the planet mass to be 23 Earth mass. And this brings it to be having a greater density than our own Neptune, but we also know it's not rocky. What's more exciting about this system is that it is one of the coolest surface temperature planet around transiting planet around the brightest stars. So if we want to study atmosphere of cool planets, this is the point to start with. We also identified a second transiting planetary candidate in the same system, which is almost exactly the size of Earth. This possible second transiting planet signal orbits the star every 8 days. If confirmed, it will be the smallest planet confirmed by TESS to date. Now I just want to put all these 3 planetary systems in a sphere around our solar system. So you can look at them in this context. In the graph, the gray circles represent the distance to Earth. All the 3 planetary systems about 50 to 60 light years away from our sun. And these are what we discovered in the past 20 years using various other transiting surveys. in the same sphere. You can see we made great progress using 3 months of data. And these are what we are going to discover at the end of our 2-year primary mission. So I just want you to take this moment in and watch this movie to zoom out a little bit and enjoy what the exoplanet field will be in the next coming 2 years. Yeah. I will leave the stage to Michael, and he will tell you about all the great other science tests he's going to do. Thank you.
All right. Excuse me. All right. My name is Michael Fosna. I am the test pipeline scientist at MIT, and today I'm telling you about opportunities for transient science with tests. I think the main item here is there's been over 100 transients bright enough that we can get good measurements of them with tests, and I'm going to show you the unique opportunities and information that TESS brings to bear studying these objects. But before we go into that, we've got to define what a transient is. So here is actual test data. On the left, you see, an image, lots of stars. The big blob on the bottom right is the Large Magellanic Cloud. That's the closest galaxy to our own Milky Way. And the thing about TESS is it's just monitoring patches of the sky for a very long period of time, looking for changes. So a good way to visualize that is with a difference image. So that's what you see on the right. That's just the difference between image 4 and image 5. And I can play this like a movie, and this is the kind of thing that TESS will see. And you see that the night sky is very, very busy. Your eye is probably drawn to the fastest changes and the brightest or the largest changes. But if you look carefully, there's all sorts of stuff, smaller and slower changes. And if you look very carefully, you'll see sources appear and disappear. And this is just what we mean by an astrophysical transient. Is for a given patch of sky, if you look at one time and then you look sometime later, you'll either see a new source or you'll see a source disappear. So that's all that we mean by astrophysical transient. There are many telescopes around the world looking at the sky every single night trying to find these things, and there's a central database that they can report their findings. So taking from that database, these are the 101 brightest that TESS can get a good measurement for. They're color-coded by the telescope that found them. And that's in just the first 4 months of data. And as we'll see, TESS can bring a huge amount of information in terms of identifying and studying these kinds of systems. And the key is that we're continuously monitoring these objects so that we have data on them before they were even discovered. Here's a very illustrative example of this. So it was an event that was reported at about 2 in the afternoon on August 3rd. So it happens to land in Sector 1, Camera 2 of TESS. So we went back to see what was happening at that time. And in fact, we see a very sharp burst of light just before the announcement of the transient, and then the smooth decay. And this is the kind of signature of a strong stellar flare. It turns out there is a very faint M-dwarf star at this location, which are known to display this kind of phenomenon fairly regularly. But the point is that TESS, if it hadn't been for the TESS data, we would never have known what this transient was. We can identify it really, really clearly. And of course, based on the brightness of the flare and the shape of the flare, there's lots of science that can be done on this source. This is a very illustrative case of the new kinds of things TESS can do. Probably the most famous kind of transient are supernovae, which are the explosions that mark the deaths of stars. So for this talk, I'm going to be focusing on a subtype of supernovae, type 1As. These are, astronomers know these are thermonuclear explosions of white dwarfs, but we don't actually have a great sense of what kind of systems cause the supernova, the type 1A supernovae. There's sort of two competing theories. In the first scenario, there's a single white dwarf. It pulls matter from a companion star, reaches a critical mass, and then explodes, just as you see in the video. The second scenario, it could be that there are two white dwarfs, and if they were to merge together, they'll again be above the critical mass, and you can get a type 1a supernova explosion in that way. In order to figure out the difference, you really need to look at the early time behavior of the system, the early time light curve. So here's an example of one that we saw in test sector 1 data. Just as a point of clarification, the break in the middle of the light curve that you see, that's where TESS turned and pointed at the Earth so we could downlink the data. But the main point is that that smooth rise is very hard to get. It's kind of the unique thing that TESS can bring to this, and that holds the keys to figuring out which of those two scenarios the type 1a is. The general sense is that if there was a companion star, you should see a bump or a wiggle in the early time light curve when the explosion hits the companion. So here is the Sector 1 first light image. And in Sector 1, we've already found 6 supernovae. So I'm going to show you their locations and what they look like. You'll see there's a big diversity. But again, what TESS is bringing is that early time measurement in order to tie down what the progenitors were like. Just to put this number of 6 supernovae in 1 month in context, the only other mission that could really do this was the Kepler spacecraft. And Kepler found 5 supernovae in 4 years of observation. So it's much more difficult to do. We already have 6 in 1 month. So again, our total mission is 2 years. So you can see we're going to have a very large sample of these supernovae and with high quality light curves, and that's going to do a lot in terms of informing our understanding of the progenitors of these systems. And that is it for the transient, so thank you.
Okay, it's me again. I can leave you to guess why I'm giving 2 presentations. I'm here to tell you about now what the people outside the TESS team are doing and why we're so excited by TESS and all the things that the science community here can bring to the space mission, both at this meeting and beyond the international community. TESS is going to be a robust planet finder. It's going to be a supernova machine. But there's so much more that TESS can do, and we're really very excited about that. And with the data release having happened, the first data release just a month ago, we're already seeing really exciting and rapid rate of discovery and new science coming out. So I'm going to show this image again because it's really a truly fantastic image that I think blew all of us away, even those of us who kind of knew what to expect from the mission. It really is fantastic. You know, this image here has over 1 million sources for which TESS can get very precise photometry. And we get an image like this every 30 minutes, almost unblinkingly, for a month. And then we move on to another field. And over our primary mission, we're going to get 26 such fields like this. That really is an astounding amount of data, really truly unprecedented in kind of planetary science, and a gold mine for people to search through. I think we learned from Kepler and then going to K2 that every time you look at a new part of the sky, you discover new things. And many of these discoveries are unexpected discoveries. So I think that's truly exciting what we have to look forward to. To put into context, you know, how excited our scientific community is here. This is just like basically a stats page that the massed archive at Space Telescope keeps, and the numbers that people interacting with the data are truly staggering. This is data from just the information from just the first week after data release. Over 1 million light curves were downloaded from the archive. Over 1 million images were downloaded of TESS data in just the first week. 67 terabytes of data downlinked. All of these things are record rates of downlink from the archive. Fortunately, they prepared themselves for such an influx of people getting data. And we're able to keep up. But it really is astounding how much data are coming out. Our scientific community was really exciting. For those of you who get on Twitter, you could follow science happening in real time on Twitter and continue to do that. And I think for a new mission happening, that's really exciting. It helps everyone see the scientific process and how it's really happening in front of our eyes, and the new discovery. Just some cool stuff that we saw. One person, tweeting how excited they are with the data. Interactions between people saying, "Hey, I saw a weird blob in the data. What's that? Oh, it's a cluster of stars. Well, is there anything interesting in that?" And then working together to learn things. That was really cool to see. The one on the right there is just for some of our friends in the audience that people were excited about the documentation. That never happens. I mean, isn't that wonderful? So really a truly heroic effort to get the data out and on time, and people to be excited how great it is. And I just wanted to throw in one of my favorite things, the Test Roulette website. I think it's test.casino. This is a really nice tool that some folks from outside of our test team decided that the way they want to interact with the data is they're going to make a website that you can click hit me and it'll show you a random test light curve. That enabled people to just quickly see a whole bunch of different sets of test data, understand what they're seeing, show off what they're seeing, and start to show other scientists and people outside the scientific community, what is the data and what it looks like. And so these kind of things happening organically from the community is just really, truly astounding. And I think it bodes well. And I think that's just how I like to see science done. Beyond the scientific community, the citizen scientist community really got involved in tests right away. We have to credit the Planet Hunters test group for being ready on basically on day one with the data release, having that website up, and then within the first week having almost a million classifications of not just planets, but also finding things like asteroids and transient sources and variable stars. I think them really getting involved and finding sources for discovery was really very exciting. As part of what we do here at NASA, we support scientists using this data beyond what the mission team is doing. The scientific community is being funded to do investigations not just in exoplanets, but also to study stellar astrophysics, things like flare stars, and also solar system objects, looking at Trojan asteroids, for example, orbiting Jupiter, and then looking beyond that at extragalactic science. So studying everything from black holes to neutron stars to active galaxies. So the range of science here is exciting, and I think it speaks very well to the team that built this amazing spacecraft primarily to study exoplanets, but knowing that this is going to be a discovery machine for years to come, and really is going to transform many missions, many science investigations. So I think I'm going to leave it there, and we're going to welcome questions. Thanks.
Thank you all very much. So we'll go now to the Q&A part. We're going to start here in the room. My esteemed colleague Frank Reddy from NASA Goddard in the back of the room has one of the microphones. Frank helped us organize this briefing, so I appreciate that. Carrie will be monitoring the webcast, and we'll take questions from the webcast in a little while. So we'll start down here with Alex. Please remember to identify yourself by name and affiliation.
Yes, I'm Alex Witzy with Nature. My question is for Chelsea. Could you go through how many planetary candidates there are? I think I wrote down more than 300 planetary candidates. And how many confirmed planets there are? I have down more than 8 planets confirmed.
Yes.
And how are those other 5 compared to the 3 you talked about here?
So the other 5, I remember there is a 8th magnitude hot Jupiter, and there is another planet that's slightly bigger than Neptune. I'm trying to remember what the other 3. Oh, there is a 7th magnitude warm Jupiter at 11 day. I can't remember the other 2, but they are either slightly bigger than Neptune or giant planets, but all around really bright stars.
And this is in addition to a very large number of previously known planets that
Yes.
that were discovered from ground-based.
We rediscovered about 14 known planets. And I know, as a matter of fact, there are probably 20 or 30 that's almost ready to be published. Yeah.
Okay.
Leslie Sage from Nature. George, in the extended mission, will you be revisiting already observed parts of the sky with different cadences to look for different kinds of transients?
I've actually got a slide that I could show that points that out if I could come to the podium. So it's at the very end. Let's see, how do I get to the very bottom?
I think well, let's launch.
I think if, yeah, there we go. There you go. This is set up. This, yeah, that'll be fine. Okay.
Okay, and then I guess we need to play.
Play, yeah. All right, that's it right there. Okay. Yeah. Okay, this is a. Okay, this is a comparison of the sky coverage that we're going to have with TESS in the 2-year primary mission, and the reason that it has that little S on its side shape is that's the ecliptic plane. This plot is in celestial coordinates, and the two orange blots to either side of the oblate are the ecliptic poles where the fields overlap. So in the 2 years that we have for the primary mission, we first do the southern hemisphere and then we do the northern hemisphere in succession. Now for the extended mission, which will last for about 30 sectors rather than 26, the idea that we're thinking of is, first of all, that very interesting gap where the ecliptic occurs was thoroughly searched by K2. And one of the things that we want to make sure is that we go back and recover the planets that were discovered initially by K2, so that many of these are associated with bright hosts, and so they're going to be important for future generations of astronomers to study. So TESS can actually, because TESS has such a large solid angle, it covers 2,300 square degrees compared to the 100 square degrees that Kepler did. It can actually do this very quickly, so we can actually cover that piece of the sky in about 9 months, whereas K2 was covering it in 3 or 4 years. In addition, there's a period. There's a slot where it shows in green in that lower plot. That contains the Kepler field, the original Kepler field in the northern hemisphere. We're going to go back and actually spend an extended observation to look at that, so that we'll be able to, with a longer baseline, be able to recover a fairly large number of originally Kepler discovered objects. And then that still leaves a small gap that is hard for us to look at, because it turns out if we look at that particular portion of the sky, it would involve the satellite looking back toward either the bright Earth or the Moon, and that's something that'll have to wait until future extended missions. One of the things that we've been able to establish is by actually going back and doing both the northern hemisphere and the southern hemisphere again, we're going to approximately double the number of planets that TESS can discover, but more than that, there'll also be longer period planets, and there'll be a lot more in the habitable zone of their host stars that'll be part of this as well. And then finally, the other thing is that because of that, in that plot that I did show, that shows the ability of the mission to look for a very long period of time, perhaps a decade, to re-examine portions of the sky. In future extended missions, we're just thinking about this, but we have not made a really definite plan. What we were likely to do is use targeted searches to look for particular objects that show up in the previous missions. So I think the other thing is that we have found that right now we do these full frame images that were discussed both in Michael's presentation in particular. We envision that that 30 minutes can actually be made shorter, so that if there are transient events with shorter and shorter time, the satellite would become more sensitive to those, and those can include things like planets orbiting white dwarfs for which there might be very brief transients, brief transits lasting only a minute or two. So the sensitivity of tests for finding even more exotic forms of planets will actually be enhanced by these types of observations.
I also had a question for Michael. The supernova light curves all looked very smooth. Mm-hmm. There was no evidence for any flaring whatsoever.
Right. So the analysis on the what are the actual progenitors is still ongoing. We're just at the stage of finding which ones we can get signals and so forth. I mean, I certainly agree with you, but it would be too easy too early to speculate on what they really are. I take that as your question. Yeah.
Steve down here in the front. Oh, sorry. We'll come back to you. Yeah.
Steve Marin, also for Michael, on the supernovae. How were those all the supernovae you discovered? Why were they all type 1A? Or you're just showing the type 1As?
Yeah, so sorry, there were actually two type 2s in that sample. And it was 6 in sector 1 and then 2 more in sector 2, although the 2 in sector 2 are 1As also. Yeah.
Okay, Dan.
Hi, Dan Cleary from Science Magazine. Just a question for Chelsea. How do you measure the orbital period of a planet, if it's 36 days, from an observation that lasts 27 days?
That planet is actually detected with all 3 sectors for data. So we have more than 2 transits.
And I also have a quick question from Michael or George as well. In terms of transient objects, I presume you just observe ones that happen to be in the sector that's observed at that time. Are there any circumstances where tests would slew to look at a particularly enticing transient source?
Well, I can answer the question about slewing. That we don't envision that we would be doing things like that for the primary mission or the first extended mission. The spacecraft has a lot of capabilities for doing things like that. By changing firmware or software, we may be able to make modifications. It actually can move and settle quite well. And then the other thing that we've thought about, but again, this is something that wouldn't happen for several years, is to actually have the satellite be able to trigger on events that it finds in the field of view and send that information back as very short, very quick alerts. All these things are possible, and as we learn to use the satellite more and more effectively, we'll certainly be interested in migrating toward those alternate forms of operation.
Yeah, and I can also add that there is something a little special about the places that TESS observe. So if a supernova went off in Sector 1, we could always go back and see what it was doing 4 months ago. And, it's something we'll certainly try and see if there's anything to be had there. But the 101 number is only things that happened during the observations. If you counted everything over, say, the last year, it would be a much higher number.
Yeah. Well, one other thing about the pointing, I think that's important, because as Chelsea pointed out, for what we call camera 4, the one that looks at the ecliptic pole, that actually has a full year of exposure. So, for example, in the Large Magellanic Cloud, if anything happens during this full year, we'll have that archival record to go back to. And the other virtue in the north and south ecliptic pole is that those are the continuous viewing zones for JWST and very likely for other future missions that are going to be operating at L2, because it's just it's really the sweet spot for satellites that are in that particular operating mode in which they have to avoid looking too close to the sun.
Okay, Lisa.
Hi, Lisa Grossman from Science News, and I was wondering if the properties of any of the new planets that you found are surprising in any way, and if they can tell us anything about planet formation or the statistics of what kinds of planets we can find where, anything general big picture like that.
So we can't tell statistically yet because we only have a small number of planets. But the planet systems are quite special. For example, for the Pi Mensa planet system, the outer super Jupiter is 10 times the mass of our own Jupiter. The orbit is fairly eccentric. The furthest point of orbit is at roughly the location of orbit of Jupiter. The inner orbit, the closest point of the planet orbit, is at the orbit location of our own Earth. So you can imagine how eccentric that is. So we don't know how that system could form in such a way with the eccentric super Jupiter outside and a probably not eccentric super Earth inside. So that would be a surprise that we want to understand in the next few years. And for our H3844b, it's, as I said, it's one of the rare population of the ultra short period planets, and we also don't fully understand how them form at such short period. For the third planetary system, it's denser on Neptune, and we haven't seen that many type of planet like that. We think it must have a substantial atmosphere, but also not rocky. So once we look at it with JWST, we will try to understand a bit more of how it formed or what the chemistry in the atmosphere would be.
I could just point out one other thing that sort of bears upon that. There's a very extensive follow-up program that's been mounted. That's part of TESS. That's being led by our colleagues at the Smithsonian Astrophysical Observatory and Harvard's CFA. And unfortunately, the key person in that group, Dave Latham, could not travel and be here. But there's been an orchestration of ground-based astronomers to carry out follow-up of TESS objects that now it's of order 300 or 400 ground-based astronomers, and they're all working very closely together to provide radio velocity data and other characteristic spectroscopy of host stars, and that's a very key part of the TESS mission that we're very appreciative of.
I'd like to go to the webcast. We'll get a couple of questions courtesy of Carrie.
All right, this question, is this on? Can
Yeah,
you hear
it's
me?
on.
Okay. This question is for Chelsea from Monica Young at Sky and Telescope. She asks, is there a publication, catalog, or online archive where there's information about the existing exoplanet candidates from TESS?
We are planning to publish one, and Natalia, who sits among the audience, will be the one who leading that catalog paper. We'll let you guys know when we put the paper out.
Is that it? Oh, okay. We'll come down here to Ethan then. Make sure you raise your hands high. I'm having trouble seeing them. Or maybe they're just not being raised.
Hi, this is also a question for Chelsea about the Pi Mensae system. Chelsea, is this the first time that we've ever discovered a planetary system with such different properties at such different distances that we've got, a super Earth, mini Neptune, even though I hate those names, planet with just a 6-day orbital period that's totally circular, and meantime we have discovered via the stellar wobble method a planet that comes almost to within the Earth-Sun distance at periastron, but farther than the Earth-Jupiter distance at astron. I know you said in the press release that this should provide us with many insights into how the system formed. Do we have any insights into how the system formed? And do we ever have another system like this?
This is the most extreme system we know has this type of architecture. We know probably 3 other systems has a inside transiting super Earth and the outside giant planet, but they are not, the giant planet outside are not as eccentric as this one, and also not as massive as this one. So we typically think when planets form, they form on circular orbit, and something need to disturb such a massive giant planet to onto such a eccentric orbit. And we are really surprised that the inner super Earth actually survived that disruption event. So we don't know what exactly happened, but it's a mystery we really want to understand.
Okay, we'll come back here.
Hi, Liz Landau from NASA JPL. Michael, I just wanted to clarify one thing you said. You mentioned that Kepler had found 5 supernovae, but that was just for the Prime mission. The K2 mission actually found dozens more supernovae, correct?
Yeah, this is correct. It's just a matter of, K2 was much later. That was it, yeah.
Any other questions? I have a couple of quick ones. Oh, Carrie, anything else online? Okay. First one is, I know you don't have enough statistics for confirmed planets, but just based on the number of candidates that you've identified so far, is that number roughly consistent with your expectations of how many planet candidates your system would find?
Yes, it's roughly consistent with our estimation. Actually, in Tom's paper, he estimated we will find about 4,000 planetary candidates brighter than 13.5 magnitude in the 2 years Prime mission. We released about 300 planet candidates from less than 3 months of data, and we will discover more per sector as the data goes on. So if you do the math, it's roughly consistent.
Okay. And then probably for George, so what, if any, consumables are on board? What is it that would cause tests to no longer be operational? Does it have, gas, or does it have moving parts, that kind of thing?
Well, the flight dynamics people who worked on providing the details for the pointing of the thrusters that had to be used to put TESS into its final orbit did a really superb job. They were very economical in their use of hydrazine, which was the propellant material that's used. We started out with 40 kilograms, and they only used 10, and that leaves 300 kilograms. Now, for actually staying in the TESS orbit, the TESS orbit is actually stabilized by something called the COSI mechanism, which is a 3-body interaction between the Earth, and the Moon and TESS. So we don't really need any propellant to stay in the orbit that we're in. We do need propellant to do momentum management with with our 4 momentum wheels. And every time we make a change in that setting, which might happen maybe every 2 or 3, or maybe every 2 or 3 days, or maybe a week, that takes 1 gram. So if you do the arithmetic, we've got enough propellant left for about 300 years on that score. So I don't think that's a problem. As far as there are no moving parts in the instrument at all, the only deployable we had were the solar panels. There are 4 momentum wheels, and they were very carefully selected for their heritage. Robert Lockwood from NGIST is in the audience, and he'll correct me if I remember the number incorrectly, but I think it's 60 million hours of on-orbit operation from these heritage wheels, and so that should last. That particular thing should last for decades. In my plot, I only put out extended missions running 10 years, but if NASA is patient with the mission and funds us properly, I think we could probably go for several decades more.
Well, we'll hope the shutdown ends in time for that.
That's right.
I just want to clarify, because I either misheard you or you misspoke. Did you say there were 40 kilograms of hydrazine or 400 kilograms?
40.
So you used a quarter of it.
We used 25%.
Okay, great. All right, well, it is 3:15, so I think we'll wrap it up there. I want to thank our presenters again, and thank Frank Reddy at NASA Goddard for helping to organize this, along with other PIOs at Goddard as well as at MIT. It is a shame that some of the team members from the Smithsonian weren't able to be here, and that's just one of the many effects of the shutdown, but hopefully that will all end very soon. So just a reminder for the press registrants, we do have the AIP press reception in this room this afternoon at 5:30. Tomorrow morning we continue. In fact, Chelsea's last answer to a question was a perfect segue to tomorrow morning's briefing, which is trying to get to the bottom of the mysteries of planet formation. So come back tomorrow morning at 10:15, and that session will be webcast as well. And we look forward to seeing you then. Thanks a lot.
Thank you.
I'm not having a good technology day. Thank you, everyone. That concludes our coverage of the AAS press conference coming to us from Seattle, Washington. All this week, the American Astronomical Society will be having 2 press conferences a day, except for Friday when they expect people are heading home. So join in for the Daily Space every day at 1 p.m. Eastern, and this will be followed promptly by the Pacific Morning Press Conference at 12:15 Eastern, 10:15. Sorry, mathing in my head. It's 10:15 Pacific. Tune in at 1 p.m. Eastern for the Daily Space. The press conference will start at 1:15 p.m. Eastern. This is 10 a.m. Pacific for the Daily Space, 10:15 a.m. for the AAS press conference. The second press conference of the day will start at 5:15 Eastern. This is 2:15 Pacific time. Thank you so much for coming. As always, we're here to put science in your brain. This is a production of the Planetary Science Institute, brought to you working in collaboration with Youngstown State University. Tomorrow, we will also have an added report coming to you from our own Annie Wilson, who is on site at the AAS meeting. So thank you all for coming, and I'm always happy to share. And this is how science is done, and this is the first stage in getting results out to the world. So wherever you are in the world, go out and explore, and remember to look up. Have a fabulous morning, evening, or afternoon, wherever you may be, and we will be back tomorrow. Bye-bye.